So, let's jump right into it. What on earth is cloud computing? Anyone have any vague idea? Yeah?
When you, what you're doing isn't just on one computer, but shared between many computers and kept them on a separate server.
Okay, that's good. That's an element of it. Any others? Yeah? Okay. Yeah, networks are always involved. We'll get a lot into that. So remind me your name again? Noel. Okay. Any other thoughts? So it's really not well defined. Cloud computing is more of a buzzword than a technical definition. So it could be a simple client-server communication. We're moving our computation over to the server. It could be some sort of ad hoc peer-to-peer. So if you connect to another computer in this lab, that could be cloud computing. Could be distributed computing, so like that, only normally it would be based on larger data centers. Could be virtual infrastructure. So a lot of cloud computing uses virtualized infrastructure. We'll get a lot into that later on. Basically makes hardware that's made in software, so we can change it a lot more easily than real hardware. The definition that we'll use for the cloud computing in this class, Sarah touched on it a little bit, is sharing computational resources. Make sense? Yes. Pardon? So this is almost exclusively software. We'll be doing a little bit of hardware right now so that you have an idea what's actually running the software, but almost exclusively we will be doing hardware or software. So there are kind of three classes of cloud computing. So software as a service. The idea is we're giving software to someone, and that software is run on the cloud, it's shared by many users, and it does a specific thing, right? So they can use the application, that's really all they can do because it's just that piece of software and it runs in the cloud. So Gmail, who has Gmail? Who has another type of email? Almost all of you, if not all of you. So that is a software as a service cloud computing application. Quicken Online is like a personal financial app, and Google Docs. Who's used those before? A couple of you. Okay. We'll do a little bit with that in a minute. Platform as a service. So that says, rather than here's this limited software you can use, it says here's a programming language you can use. So you can log in, write your Python, and run it on the cloud. That's platform as a service. So Google App Engine, for example, lets you do that. And finally, we have infrastructure as a service. So that uses that virtualization, and it says you can log in, and it's like you're at your own server there. It's virtual, but for as far as you're concerned, it's your own. So it's another computer on the cloud. You can do what you want with it. You can do all kinds of computations. We'll be using infrastructure as a service very extensively in this course, specifically with the Amazon Elastic Cloud. Any questions? So when you go and make a presentation online that you can share and collaboratively edit with your peers, which one of those is that? Right. So these ECF machines, you can actually log into those from home. Which one of those would that be? Sarah? Yeah. Yeah, so that would usually be infrastructure. Could be platform if they limit what you can do. In this case, it is infrastructure. Yes, Noel. Dropbox is software. Yeah, because it does a specific thing that is sharing files. It has to have some programming capability to be platform or infrastructure. All right, so the basic element that almost all end-user cloud computing uses is this client-server model. So a client is you. It's the person who's using the software, and it's generally just a computer with an internet connection. It could even be your phone or your refrigerator. In fact, there have been instances of refrigerators being hacked before because they are getting a lot smarter and people are catching on. So they can tell when you went for your midnight snack. Not quite to that amount of detail, but it's an interesting problem. The server is just a computer. Servers aren't these big fancy things that you see in movies. They can just be a computer. And it runs a piece of software that says, listen for a request for a web page or for a service and send it back to the client. So let's start off with a very basic client-server interaction. So are you all logged in? No? So let's do that, and put your hand up if you have any trouble with that. Maybe counselors just kind of keep an eye, make sure everyone's doing okay. Put your hand up if it's logging in or logged in right now. Put your hand up if you're having trouble. I'm not seeing the whole class represented here. Counselors, does everyone look okay? Okay, so some of you are still getting logged in. Some of you, yeah, so when you are, open up your favorite browser. I think we have Chrome and Firefox on here. And just go to a website. Who's going to be doing what websites? Yeah, I saw a hand back there. Remind me your name? Francois. Where will you be checking out? YouTube? Okay. Don't get too distracted on it. The point is to understand what's going on behind the scenes when we go to YouTube. Anyone going to just Google? Anyone going to Facebook? Please don't. You'll get distracted. Put your hand up if you are done. You've got it? So that is an example of a basic client-server interaction. Counselors, do you see anyone who's still having trouble logging in? So let's think about what's happening behind the scenes here. We are connecting to the internet, we're sending the request for the page over the internet, the server is receiving that request, it's sending the page back, and then we're getting it in our browser, getting the code that says what the page should look like, and rendering that page as you see it on screen. That's a very involved process, and we're going to be looking a little bit more detail into that this morning. And it's something that really sets the foundation for the rest of cloud computing. So let's start by using a basic software as a service cloud service. So you'll notice in your shared folder is in My Computer. So if you open up My Computer, the S drive, Courses, and Deep 2014. There should be a links.txt. So open up links.txt and head on over to that URL. Yeah. Oh yeah, so it might not show as .txt, just links then. So I will open that up right now so we can see in real time what everyone's doing. Noticing a lot of you guys on there. So for those of you who haven't used Google Docs before, what do you think of this? You can see all the names. They're all showing as anonymous, but the anonymous names of everyone logged on. You can see them making the edits in real time. This is a basic example of software as a service. Nom 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 nom. Varun, I like yours. Any questions on how this works? Not yet. You will have some once we get a little bit more into the implementation technology. So we'll leave that open for now, but head on back. So that's software as a service, right? So that's a very helpful thing when you're editing a document or a report in a group. And you can see how easy and intuitive it is because Google does a very good job of making it work well. We'll primarily be using infrastructure as a service to make our own software as a service throughout the week. You guys excited to do that? Anyone having any ideas pop into your heads as to software as a service you want to make? It'll come. So that's the basics of cloud computing. We will now get into how it all works. And that's where we'll do a little bit of hardware, not much. So, how do computers work anyway? Do these look familiar to anyone? Okay, see a couple nods, couple very vigorous shakes of your head. These are logic gates. So, a logic gate takes two of what's called a Boolean value. Boolean, you've probably not heard of if you haven't heard of a logic gate. It is just true or false. So you know how we have integers, they can be whole numbers, we have real numbers. Booleans is just true or false. And in computers, we represent those as zeros and ones. So it's like an integer, but just 0 or 1. A NOT gate takes it and flips it. If it gets a 0, it puts out a 1. If it gets a 1, it puts out a 0. An OR gate puts out a 1 if either this or this is 1, and an AND gate puts out a 1 if both this and this is 1. Make sense? So that's the basics of how a computer works. You probably heard a little bit about that and thought, like, that's nice. How does that make Gmail? Right? There's kind of a bit of a disconnect there. And we'll be getting into that. So to begin, how do these gates even work? What we have, you're all familiar with basic circuits, right? So you know about resistors and switches and grounds? So what we have for the NOT gate is initially 1 volt is wired up to the output. So we're assuming that 1 volt is our 1, 0 volts is our 0. If we put a 0 on the X, this switch will be open, and then we put out a 1. If we suddenly put a 1 on our X, then this switch closes, this is wired to the ground, and this resistor makes it so it's more to the ground than to the 1, and we end up getting a 0 out. Does that make sense? Right? So we need that resistor there so we don't short circuit it, obviously. For OR, now it's by default wired to 0, because with both of these off, both these switches open, we want 0. If either this or this are closed, and switch closed, by the way, means it's turned on, then we get a 1. And with the AND gate, they both have to be closed. Make sense? But there's a bit of a disconnect here. How did these switches get controlled by these wires? Any ideas? No? Word transistor ring a bell to anyone? All right, so a transistor is what we use in modern computing. Initially, they were mechanical, and in fact, they were mechanical switches, work just like the ones in your wall, except they used a magnet to switch them. So we put a current through one wire, that creates a magnet, and that pulls a piece of metal that closes the switch. And then they had vacuum tubes, which worked very similar, except it changed the conductivity of a vacuum to do that. Now we use transistors. They're much faster, much smaller, much cheaper, and they allow millions upon billions to be put inside these tiny CPU chips that you have in those computers there. The basics of how a transistor works is they are made of semiconductor lattices. So this is silicon, where the name Silicon Valley comes from. It's the basis of transistors. And what we do is we do what's called doping them. So we put either a phosphorus or a boron in every couple atoms, so a couple impurities into it. And that creates either an extra electron or a hole where there isn't an electron. Does this ring a bell to anyone from chemistry? A little bit? Yeah, so in chemistry, you know that what causes conductivity in, say, a metal is the electrons aren't really bound, the electrons aren't really bound to any one atom, right? So they can free around, it's like a sea of electrons. In a semiconductor, with just silicon, it's more like an insulator, right? So it's more like those covalent bonds, they're bound very tightly and they can't actually flow. Adding these impurities allows them to flow. What happens is there really aren't enough of them to flow. So it's like a little bit of conductor mixed in with a lot of insulator. And that means that normally, when we have these different types of semiconductors, it doesn't connect, it doesn't flow. But if we put a little bit of electricity on the gate here, a bit of voltage, yes? Oh, do you have a question? Sorry, looked like you did. Voltage causes electrons, since electrons are charged, it causes them to move, right? So it's like electrostatics, if you stick a balloon to the wall, like that, except instead of balloons moving, it's electrons. And it causes either the holes or the electrons, depending on what type is here, to move up to the top. And then suddenly we have enough that it's like a sea of electrons or a sea of holes, and they can flow. And that's what closes the switch. That makes sense so far? So what we have is we start out with this magnetically controlled mechanical switch, and we move over to the transistor. And that's what it looks like. It has these two that are controlled by a switch, controlled by this. Yes, Sarah?
So if it's a 0, there's no electricity flowing through, the switch is open, and if it's a 1, there is electricity flowing through, and the switch is
Exactly.
closed.
Yeah.
Okay.
Yeah, so we can actually then take these mechanical switches, change them to transistors, and wire them up to the inputs. So as Sarah was saying, if we have a 0 on here, this switch is open, the output's wired to a 1. If we have a 1, the switch is closed, the output's wired to a 0. And the same concept applies to the OR and the AND. So that is how, from the semiconductor level up, gates work. Now we get into binary. Who's familiar with binary? Okay, Sarah, you know everything so far. Anyone else? So binary is based on zeros and ones, so like that Boolean system we were getting into before. And it's similar to decimal. So remember way back to grade 1, how we have the tens placed, the ones placed, we might have the hundreds placed down here. And we use this little subscript 10 to represent that this is a decimal system, it's base 10. In binary, we have our ones place and our twos place, because it's base 2, right? And since 10 is, or 100 is 10 squared, 2 squared is 4. And 1,000 is 10 cubed, 2 cubed is 8, right? Notice it's times 2 each time. So we have a 1 in our 64's place, plus a 1 in our 32's place is 96, plus all these zeros, and then a 1 in our ones place makes 97, right? So what, say, would be the binary representation of 43? Anyone think you know how to figure that out? 43, yeah. Yes, or remind me your name?
It's Velo.
Pardon?
Velo.
Velo?
Yeah.
Okay.
The 128 and 64 would be 0.
Good.
Then the 32 would be 1.
Right.
Then 16 would be 0.
Okay.
8 would be 1. 4 would be 0. And 2, 1 will be 1s.
Right, so we have 32 plus 8 gives us 40, and then plus 2 plus 1 gives us 43. Does everyone follow that? So in this case, we have 51 as another example. We have 0, 0, 32, 16 makes us 48, and then we add 3 to that to get 51. And we can actually go ahead and add binary numbers just as we add decimal numbers. So here we're adding 97 plus 51, right? 7 plus 1 is 8, 9 plus 5 is 4, carry the 1, and that just gives us 148. In the case of binary, 1 plus 1 is 2, but what's 2 in binary? Yes? Sorry? Yeah, 1, 0, right? So we have a 1 in our 2's place, a 0 in our 1's place. So remind me your name? In the blue shirts? Pardon? Julian? Okay. I'll try to get your names by the end of the day. Yeah. So 1 plus 1 is 2, which is 1, 0, so it's 0, carry the 1. And then 1 plus that carried 1 is also 1, 0, so we stick that here because 0 plus 0 is 0, right? Then 0 plus 0 is 0 again, 0 plus 1 is 1, 1 plus 1, and again we get our 1, 0, so 0 carry 1, plus 1 is our 0 again, carry 1, and then we get this value. Yes?
Is it always by a factor of 2, or is that just this one example?
You mean these place values? Yeah, it's always by a factor of 2. It's like how 1,000 is greater than 100 by a factor of 10, and then 10,000 by a factor of 10 again. In base 2, it's by a factor of 2. So I went through that fairly quickly. Does that kind of make sense, how we got this value from these two? Right? And now we can take a look at what it's equal to. Well, 1 in the 128's place, 064, 032 plus 116. So 128 plus 16 is, I can't math, 144. And then we have a 0 in the 8's place and a 1 in the 4's place. So 144 plus 4 is 148. And that gives us the correct value in binary. Making sense so far?